Hello everybody. Today we are going to discuss ZEEMAN effect. In the earlier classes, we studied space quantization, and before that we discussed that how a particular atom placed in external magnetic field, how the magnetic dipole moment starts to interact with the external magnetic field, and because of this external magnetic field, the magnetic dipole moment experiences a torque, and due to that torque, because of that torque interaction, the angular momentum of the loop or of the electron starts to precess around the magnetic field, external magnetic field, right? And because of this interaction, now there will be some kind of phenomena in which energy will further get splitted. Energy lines will be further get splitted in different lines, and the energy particularly will the transition happening from one state to another state will not only depend on the principal quantum number n, but will also depend on ml, and we are going to focus on that today. Okay, so ZEEMAN effect, firstly it was proposed by ZEEMAN in 1896, and according to ZEEMAN effect, when a light source which is giving a particular line spectrum, in which when electron jumps or electron jumps from one quantum state to another quantum state, it emits out a particular electromagnetic radiation, because according to Bohr principle we already know that if electrons are in a particular state, moving or accelerating or revolving in the particularly in some particular orbits, like circular, or maybe those orbits may be elliptical one, but if they are revolving or they are oscillating, then any oscillating charged particle, according to classical mechanics, any oscillating charged particles emits electromagnetic radiation, right? But according to Bohr principle, and we also saw the elementary results before that, so according to Bohr principle, the electrons revolving in those particular orbits does not radiate anything, and does not radiate. So if they do not radiate, then what happens when electrons transmit or electron go under the transition from one state to another state? So this is according to Bohr correspondence principle, that if electron goes from one quantum state to another quantum state, the stationary because of this transition, the radiative transition happens, and when electron converts its position from one quantum state to another quantum state, it starts to radiate. It radiates, or it absorbs the photon to do the transition. Okay, so we already discussed that radiative transition, right? So for a particular line spectrum which is coming out of those radiation, when electron gets transmitted from one quantum state to another quantum state, now this line spectrum or the frequency of this line spectrum depends on the principal quantum number, that from where to where the particle is going, right? So in the when we place this atom in the external magnetic field, what happens, that the spectral lines emitted by the atom of the source are splitted into a number of polarized components, some number of polarized components, or we can say that line got splitted into different another lines. Okay, and we are going to discuss this. But for ZEEMAN effect, the interactive field, the external field, must be very small in magnitude. Now this is the most important thing, that the field must be a weak field. It should be some several tenth of the 1 Tesla. Why should it be small? Because then there will be another factors, and we are not going to discuss that, like Paschen-Beck effect. Okay, so that thing is not in your course. So for ZEEMAN effect, this particular phenomena we will look into, and for ZEEMAN effect, the magnetic field should be a weak field. So how does it happen? Why the energy levels got splitted into many energy levels? and why it happens. The radiative transition depends on magnetic quantum number. Now we are going to discuss this. First of all, any electron which is revolving around the nucleus, any electron in a particular orbit, that particular electron acts like a magnetic loop, current loop, and because of that current loop acts like a magnetic dipole, and that dipole has some magnetic moment, and that magnetic moment experiences when we place the atom in external magnetic field. So that magnetic moment experiences torque, because any dipole which is placed in external magnetic field will experience some torque. Like if we consider electric dipole, then electric dipole will also experience electric dipole moment will also experience a torque when we place the electric dipole in a external magnetic field. Similarly, when we place the magnetic dipole in external magnetic field, it will also experience a torque, and that torque interaction we discussed this already. So the magnitude of that is torque is equal to mu L cross B, where mu L is the magnetic dipole moment and B is the strength of external magnetic field, right? So that also depends on the angle between them. So torque is equal to mu B sine theta. Now, because of this interaction, magnetic energy gets stored, which depends on both the magnetic dipole moment and its orientation with respect to the external field. Now, what is the energy stored? If we change the orientation, then that torque is going to change, because torque also depends on angle, and the total energy stored in the interaction is this much. Mu m is equal to minus mu b cos theta, right? We will do the integration with respect to this, so we will get that this term, that mu m is equal to minus mu b cos theta, and mu is the magnetic dipole moment. So when the interaction energy or the potential energy stored in the system, when this potential energy is minimum, whenever mu is parallel to b, the mu m interaction energy, whenever the theta is equal to 0, this interaction energy is the smallest one, right? This is minus mu b, and torque experienced by the dipole moment will be maximum when the angle is 90 degree. Okay, so which means mu tends to align itself in the direction of B, because the system will try to tend its to take to or gain the minimum energy state. But it cannot happen as well, because when we were discussing about the space quantization, we discussed that angular momentum can never be parallel or anti-parallel to the external magnetic field, because that thing is limited by Heisenberg uncertainty principle. That thing is limited by Heisenberg uncertainty principle, right? So which means that mu tends to align itself in the direction of B, but it is also limited by the discrete condition. So this cannot happen as well. So as we know, electron magnetic moment mu L is equal to minus E by 2m L. We already deducted this result. So in terms of magnitude, this is equal to this much. If we put this value into this equation, we will get that mu m, the magnetic energy, um is equal to this much, which is depending on L magnitude, B magnitude, and cos theta, the orientation of L with respect to B, right? So here energy depends on both B and theta. Now if B is in a particular direction, z direction, and L is making some theta angle with this, then cos theta, we already know that cos theta is equal to this much. Now cos theta can only take some specific values, and this is already limited by this formula, that L, when we take the projection in the direction of magnetic field, when we take the projection of angular momentum in the direction of magnetic field, then that projection is Lz, and Lz is equal to L cos theta, right? So the cos theta is limited by Lz and L, because Lz can only take some specific values, which is the eigenvalues of Lz operation is ml h cut, and the magnitude of L is equal to root of L into L plus 1 h cut. Now these are limited by these quantum numbers, right? So the angle of the angular momentum with respect to the magnetic field, or the angle, this is also the space quantization concept, and we already discussed this thing. Okay, so let's move further. Now this cos theta is limited by these quantum numbers, right? So let's put this angle cos theta into the energy relation we got. So we will get the energy stored is equal to ml E by 2m h cut b, right? So this is important result. This is the energy of interaction between the magnetic dipole moment and external magnetic field, and the value of this is magnetic energy that an atom of magnetic quantum number ml has when it is in an external magnetic field b, right? So this is E h cut upon 2m is a Bohr magnetron atomic unit constant, which is the value of this is equal to this much. Joule per Tesla is the unit of this, right? So the most important thing is we are going to discuss that in a magnetic field, the energy of a particular atomic state depends on the value of ml as well on that of n. Now from this result we can see that the energy is depending on ml, not only on principal quantum number. Actually it is depending on ml as well, and this is the interaction of when this happens when we put the atom in external magnetic field. This happens in when we put the atom in external magnetic field, then the energy of a particular atomic state depends on the value of ml. Okay, so a state of total quantum number n breaks them into several substates when the atom is in a magnetic field. Initially, for a particular state, the energy level was a single one, right? For a particular quantum number n, for a particular principal quantum number, we had energy as a single line, right? But now when we place the atom in external magnetic field and their energies are slightly the energy lines get splitted into different substates or different sub levels, right? Because ml values n n can take some l values, and l can take some 2l plus 1 times of ml values. Ml can have 2l plus 1 values, or right, which varies from minus l to l, and we will discuss this in further portion. So, and the energy of these levels after we place the magnet atom in the external magnetic field, the energy of these levels got splitted. The energy of these levels are slightly more or slightly less than the energy of the state in the absence of field. Now this phenomena leads to the splitting of individual spectral line. Every spectral line is getting splitted into different spectral lines, and when atom is placed in the external magnetic field. Now when we can see these spectral lines, we can see these spectral lines only when the atoms radiate into magnetic field. Now there are energy levels, and these energy levels according to ml got some discrete values as well. These energy levels got split into different energy levels. But how can we see these lines, these spectral lines? We can see these spectral lines when electron from a particular with some particular quantum number gets transited to different quantum number state, and only then electron radiates the energy, right? And this is also the Bohr principle. When electron transmit from one quantum state or some pair of quantum numbers, from one pair of quantum numbers to another pair of quantum numbers, it emits radiation, right? So the spacing of these lines depends on the strength of magnetic field, and we are going to discuss that how and how these how we can draw these energy levels, right? So the splitting of spectral lines by a magnetic field is called as, now this phenomena, the energy line splitting, is known as ZEEMAN effect, and this can also be said that this effect is a vivid confirmation of space quantization. Okay, because this effect is showing some discrete orientation of angular momentum, and because of that discrete orientation, we are we are in adequate information that with some adequate information that energy levels got splitted when the interaction happens between angular momentum and external magnetic field. Okay,